Hey everybody, welcome back to Young Engineers of Today. Sorry about the technical difficulties, although I'm glad you guys were able to see the message on Edmodo and get signed up for the classes. So that's good at least. So we got a couple of temporary classes set up for today and Wednesday, and then keep an eye out for an additional email either later on this week or uh, hopefully very early next week that will contain a link for classes for the foreseeable future, perhaps for the rest of the semester, although I can't necessarily make make that promise exactly, but it's possible. I don't remember off the top of my head exactly how long invitations for GoToWebinar last, especially when they can just sometimes kind of drop themselves like these did. But anyway, at least you're here. We'll spend some time with OpenRocket. We'll finish off our rocket. We'll probably finish off our rocket today, and we'll probably spend Wednesday running simulations on it. And then next week, we'll get right back into running our other Rocketry presentation. So we'll go through all that stuff, and then we'll probably be done with model Rocketry. So I suspect we probably have, after this week, 1 to 2 more weeks, and then we'll move on to another topic. Anyway, let's go ahead and let's spend some time reviewing what we went over. Right, Cohen, I apologize. I just got wrapped up in other stuff last week. It's still downloaded. It's just, for some reason, your computer is not associating Java files with the Java runtime environment. I did actually look it up. Yeah, it happens. I still could have sent you an email. I did actually look up a means to fix it later on that night. I have a very wonky sleep schedule because of my other job, and I figured you might not appreciate an email at 5 o'clock in the morning. So I could. Do you remember how I was setting it up so you could open up that file, like the open with? Okay, well, here. Let me just say this. Under open with, I'll just go ahead and show you. If I look for another app on this PC, I'm interested in Java's program. So I'll go into the JRE. If I go into the binaries, I want this Java W. That's what I want in order to be able to open this stuff up. And that should be what you need in order to be able to open up OpenRocket. So again, you want to right-click on it and select Open With, then choose Default Program. It'll give you a couple of suggestions. You can hit more options, scroll down to look for another app, and navigate to the Java W inside of JRE 1.8.0121, and that should open it up for you. But yeah, you can fiddle around with that. In the meantime, go ahead and get OpenRocket open, and we'll spend some time reviewing what we went over a couple of weeks ago. At this point, I guess it was last week, but regardless, we'll spend some time going over that. So you guys at least can be refreshed on everything. So let me go ahead and open up. Whoops. There we go. Our sample rocket. This is what we had so far. So we had the nose cone, we had the body tube, we had the inner tube with the motor mounted in there, and we had the fins. And that was pretty much it. But it was a decent amount of stuff. So it also introduced us to the customization windows whenever we added a new component. So as you can see here, for instance, the nose cone, we can customize the shape of it, the length of it, the diameter of it, the thickness of the wall inside of the nose cone. Because remember, the very inside of the nose cone is hollow. By adjusting the wall thickness, we can adjust how hollow or solid that nose cone is, which is good for us. We also created a shoulder, which is this little plug right here. It's essentially kind of, you can think of it like a cork or something like that. This is meant to be slotted into the body tube in order to, make sure that the nose cone is solidly in there, which is why we created it. It's got a diameter of 2.3 centimeters, which is exactly the diameter of the body tube on the inside. It's got a length of 2 centimeters, so it's inside of the body tube a little bit in order to provide some stability and grip and stuff like that. And then the thickness is 0.2 centimeters. Again, this has to do with the fact that the inside of the shoulder is also hollow. So this whole area in here is just open air. Likewise, we looked at the body tube. You've got the body tube length and the outer diameter and the inner diameter and the wall thickness. So it's got an outer diameter of 2.5 and an inner diameter of 2.3 and a wall thickness of 0.1 because again, these are three different parameters, and we can mess with two of them, and then the third one will automatically update itself so that it makes sense. Because if you have an outer diameter of 2.5, which is the outside of the walls, and an inner diameter of 2.3, which is the inside of the walls have to be 0.1 centimeter thick. Otherwise, it doesn't make any sense. Like, how many of you are fans of Doctor Who? Show of hands. Or have heard of it or anything like that? Okay. Well, you might be tangentially familiar with it. Basically, the Doctor has this time-traveling machine. It travels through time and space. It's called the TARDIS. And it looks like a regular old British phone booth back in the day, like a little police call booth. Not even a phone booth, just like one of those police booths. And, it looks like it could maybe fit two people standing. However, on the inside, it's got like a million rooms and they're all just, it's basically like larger than the largest mansion. And the comment that everybody makes when they step inside of it is, wow, it's bigger on the inside, because the outside of it does not suggest anything to how large it is on the inside. In fact, it doesn't make any physical sense for it to be that large on the inside. That's the whole thing. It doesn't make any physical sense, and that's part of the charm and the whimsy of everything, Same principle here, except we are unfortunately bound to the laws of physics. So if the outside is a certain size and the inside is a certain size, and the difference between these two is the wall that makes up the shape, then the wall has to be a certain size. Otherwise, it doesn't make any sense. If we have a square room that measures 50 by 50 feet on the outside and 48 by 48 feet on the inside, we better make sure that those walls are 1 foot thick. Otherwise, we've somehow broken the laws of physics. You can't have walls that are thicker than, anyway, you get the idea. So there are quite a few of these parameters that exist in the different components where they have like 3 related parameters and you can mess with 2 of them, and the third one is just going to automatically update. So for instance, I can make this 2.4 and it will automatically update the wall thickness to 0.05. I can make it 1, it will automatically update the wall thickness to 3/4. I can make this 0.3 or 0.3 and it will automatically update the inner diameter to 1.9. But anyway, we want it to be 2.3. We want the wall thickness to be 0.1, just all around. We also added a fin set, in which we could mess with the number of fins as well as their position on the body and whether or not they had like a torque to them. So like if I were to turn this fin cant all the way up, as you can see, they kind of have a, they're sort of diagonally mounted on the rocket, which will make the rocket spin as it's ascending. Sometimes we want that, sometimes we don't. We'll certainly have a pretty decent amount of stability. However, this will greatly increase the drag of the rocket if we have those fins canted. Largely up to you. I mean, you know, at some point you're building a rocket and you want to make sure that you're building a rocket that is stable and also will go high. So if it requires you to cant the fins maybe a little bit, then there you go. The chords are basically the lengths of the fin along this axis. So the root chord is the length of the fin closer to the body, whereas the tip chord is the length of the fin closer to the tip. The height of the fin is the length of the fin along this axis. So from base to tip, how long it is. The sweep length has to do with the length of this area right here, and the sweep angle has to do with the angle right here. So, you know, there are a number of different values that you can adjust on the fins. You can make them, you can increase the sweep on them and make them more dramatic looking. You can, you know, adjust the length of the fins and the thickness of them and all this stuff. Speaking of, the thickness value here is for the thickness of the fin. It's actually, if you're looking at the fin from this angle, this thickness right here adjusts the size of that. The fin cross-section has to do with the shape, the general shape of the cross-section, because this is the cross-section. We have it rounded. It doesn't really look like it here, but you know, it should be rounded. And we also have the component material and the finish and all that good stuff. And finally, we had the inner tube. Go back to the side view, which is the purple thing that sits inside of the body tube. And this is, as you might imagine, an inside tube inside of the body, an inner tube inside of the body, a smaller tube inside of the body, whatever. I'm just saying the same thing. But, you know, hopefully that helped clarify things. It's got a smaller diameter, obviously, because it's sitting inside of the body. So it's got an outer diameter of 1.9 centimeters and an inner diameter of 1.8 with a wall thickness of 0.05 centimeters. So it's a very, very thin little tube there, but it's basically just meant to hold the motor. And that's actually what we put here. We check this little box saying that the component is a motor mount. So any motors that we place into the rocket will get mounted inside of this inner tube. We also changed its position relative to the bottom of the pair component. So as you can see here, we added 0.5 centimeter out the back of the rocket. So the motor mount, this purple bit, or excuse me, the inner tube, this purple bit, is hanging out 0.5 centimeter beyond the back of the rocket. On top of that, we also said that the motor was hanging out 0.3 centimeters beyond the back of the inner tube. And we made this, well, because this makes the motor removable once it's spent. You know, we can take a pair of pliers or something like that and pull the motor out with the little bit that it hangs out beyond the inner tube. And also because we have a little bit of overhang so that it does not damage the back of the rocket with its, you know, with its backfire. You know, the flames and stuff like that that are coming out of the motor when it's ignited and burning fuel. That's going to generate heat, and so we want to make sure that we aren't, you know, charring the fins or like the back of the body tube, because that certainly hurts the rocket's chances at being reusable. So there are a couple of reasons why we do that. Makes it easier to remove and also, you know, increases the life of our rocket. Then when we did that, we messed around with the motors and configuration just so I could show you the menu here. So as you can see, we've got our motor mounts list over here on the left-hand side. We've got body tube and inner tube. If we check out body tube, we can actually have this component be a motor mount, but we don't. It's unchecked because we don't want to have a motor inside of the body tube. We want to have a motor inside of the inner tube, which is inside of the body tube. So for that reason, it's unchecked. However, the inner tube is a motor mount, so it is checked. Exciting stuff, right? And then, of course, we set up a motor in there using an Estes rocket motor. I swear I'm not trying to, just be free marketing for Estes. It's just, this is a brand that we all know, and, we're going to be adding a few more motor configurations. We're going to be using the same brand so that we have some sort of control among the different groups that we have. But anyway, as you can see here, we've got a configuration here, and it tells us this is what we have mounted in the inner tube. If we had multiple motor mounts, it would tell us what we had mounted in each motor mount. That would change the configuration name as well, but we're just interested in this one right now. So for as a bit of review, you notice I've got this A83 here. All of that all refers to the classification of the motor, right? So if we're looking at these in parts, what does the A represent? Yeah, the class of the engine. Basically, the amount of power that the engine puts out over its entire lifetime. How does this stack up compared to, say, a B-class motor? That is to say, how much more, or yeah, it's smaller and less powerful. By how much? But yeah, that's close. It's not a magnitude of 10. It's actually only a magnitude of 2. So that is to say, a Class B motor is 2 times as powerful as a Class A. Class C is 2 times as powerful as a B and 4 times as powerful as an A. D is 2 times as much as C, 4 times as much as B, 8 times as much as A. You get the idea. Each one is a power of 2. So that, that kind of, yeah, exactly. That can kind of make it a little bit easier to remember. If it helps you remember it at all, there are classes smaller than A. They're called 1/2 A and 1/4 A. Because we don't have letters that are lower than A. So I had to go somewhere when we're making a smaller engine, but they used J. Actually, J is much more powerful. Let's see here. A, B, C, D, E, F, G, H, I, J. It's 2 to the power of 10. Since it's the 10th letter in the alphabet, more than 100 even. Let's see here. 2, 4, 6, or 2, 4, 8, 16, 32, 64, 128, 256, 512. It's 512 times more powerful than a Class A engine. Yeah. Yeah. It's pretty dang powerful. So yeah, that is a pretty significant step up in power. How about that first number? What does the 8 represent in this particular example, or in general even? Yeah, in essence, yeah, it's referred to as like the average thrust or the average impulse. So the letter refers to how much basically power is stored in that engine. Um, so over the entire lifetime of an engine, it will put out a specific amount of power. Um, the number refers to how quickly it expends that power. So how much power it is putting out in a given second and how quickly that motor burns out. So let's say an A puts out, 150 it will burn pretty slowly, but also pretty weakly. So let's say for instance, just pulling numbers out of the air here, don't take this like seriously or anything like that. But let's say an A puts out 10 joules of energy over its entire lifetime. Watts can be thought of as how many joules you get in a second. So, or in a specific period of time, I believe it's seconds though. So 1 watt would be 1 joule per second. If A puts out 10 joules over its lifetime, but only lasts 5 seconds, well, it's putting out 2 watts a second, right? It's putting out a specific amount of power per second over 5 seconds. Now, there are Class A motors that can put out, that can last 10 seconds. They'll only put out 1 watt a second, though. So in that sense, their average power is kind of like half that of, I guess. I'm a little bit fuzzy on my math right now. For some reason, it's just my brain and math are not mixing. But it's burning more weakly, but it's lasting twice as long. It's in fact burning with half the power per second, but it's lasting twice as long. And over the life of the entire engine, it is putting out the same amount of power as that other one that burns with half the time. You get what I'm putting down there? So that's what that number represents. The higher that number is, the more powerful that engine burns at any given moment. However, the faster it burns through all of its fuel. So, and when you said that, Cohen, how quick will an engine burn if it's a number 3? I don't have the specific numbers for you, but it will be much weaker in any given moment than an 8. However, it will burn for more than twice the length of time, because it's meant to be sort of a linear relation as well. So an 8 will put out a specific amount of power in any given moment and burn for a specific length of time. A 3 will burn with less than half of that, but it will last for twice as long. At the end of the day, they will put out the same number of joules. So, that's if they're both A-class engines, that is to say. They'll put out the same number of joules over their entire lifetime. Weird, right? But it makes sense. It gives you some idea of how powerful an engine is and how long it's going to last. So the higher a number is, the more powerful an engine is in any given moment. However, the shorter it will burn before it runs out of fuel. An 8 in this case is not, I mean, it's sort of an average-ish number, kind of. Like average is relative. So, I mean, if you're dealing with rockets that are, 3s and stuff like that, 3 is going to feel average to you, and 8 is going to feel like it's super powerful but super short-lived. So it's all fairly relative in the end anyway. So it's not like we can say like, oh yeah, 10's a good baseline to work off of. Everything's based around 10, because it's not really. At least not to my knowledge. But anyway, what about that number after the dash? What does that represent? In this case, the dash 3. Oh, gotcha. I thought you were asking me how quick a 3 will burn relative to an 8 or something like that. Oh, this actually refers to the length of the delay charge. So basically, how long the engine will let the rocket coast between when it runs out of propellant and before the ejection charge blows. So a 3 will run for 3 seconds between when it runs out of fuel. Yeah, no worries. Between when it runs out of fuel and when the ejection charge blows. And that's very straightforward. Excuse me. It's very straightforward. That's just measured in seconds. So an A85 will, the delay charge will be 5 seconds long. So it'll coast for 5 seconds before the, ejection charge blows. An A86, 6 seconds, a 4 seconds, a 2 seconds, and an 8 seconds. It's a fairly straightforward number, because that's just how long it is in seconds before the ejection charge blows after it runs out of propellant. I agree. No worries. Were you not sure your keyboard was working? Or just venting some frustration? Oh, yeah, no, all good. I've been in situations like that before. So yeah, that's what all those numbers mean. Oh, I see. So that's what. That's not good. Well, that's what all those numbers mean at any rate. And we've also got some preliminary values around here, including these little circles here. Oh yeah, I get you. Does anybody remember what these circles are? No worries. All right, so the circles represent our center of gravity and center of pressure, respectively. The blue one with the quarters is the center of gravity, and the red one is the center of pressure. Uh, if you all remember, the center of gravity has to do with basically where the sort of the middle of the weight distribution of the rocket. If the back gets heavier, the center of gravity will move towards the back. If the front gets heavier, the center of gravity will move towards the front. Yeah. Um, if we were to theoretically speaking, throw this rocket, the rocket will trace an arc using its center of gravity. So the arc will be, drawn by its center of gravity. The rocket will also spin about its center of gravity. This is, of course, assuming that it's done in a vacuum. Stuff like wind resistance and stuff like that is going to mess with how the rocket flies in that respect. Enter center of pressure. So that's why we have to keep track of both of these, because the rocket is not flying in a vacuum. The center of pressure is the point about which the rocket rotates when all of the forces are acting upon, like drag, are acting upon the surfaces of the rocket. So that is to say, between the nose cone and the fins, as those work to correct either the rocket's flight or, a crosswind or something, cross breeze or something like that blows on it, whatever, it will rotate about the center of pressure. So we generally want the center of pressure to be behind the center of gravity like we've got here. And there is a certain distance we want the center of pressure to be behind the center of gravity, which is measured in calibers. Generally, we want it to be 1 to 2 calibers behind the center of gravity. What happens if it's in front? You just have a very unstable rocket. It doesn't do so well. It's not gonna have a very easy time of correcting itself. It won't. Well, the rockets that we're working with, no, certainly not on their own. It could fly into the ground, which would be bad. But larger rockets, theoretically, you could run into yeah, you could run into like a catastrophic harmonic state or something like that, which would, uh, cause a rupture in the fuel tanks or something like that, and cause the fuel to be exposed to open air, and then there could be enough friction to ignite the fuel that's exposed to the open air, and then the rocket could theoretically explode. It's sort of like what happened to Challenger, but that didn't have anything to do with the center of mass versus the center of pressure. That was just because it was a cold day, and there were a series of failures that should have been caught. Well, they were caught, but they should have been addressed. But in order to save money, they went ahead and launched it anyway. And then you have situations like that. But yeah, so you could theoretically with larger rockets have that sort of thing happen. But we want to have the rocket be about 1 to 2 calibers behind, or excuse me, the center of pressure be about 1 to 2 calibers behind the center of gravity. And a caliber is nothing but the same length as the diameter of the rocket at its widest point. So, whoops. Let me go ahead and redraw that line. There we go. That right there is a caliber. The circumference, yeah, would be all the way around. But we want it to be the diameter of the, yeah. Whoops, what am I doing? This is what I'm doing. So as you can see here, handily it gives us a measurement in calibers already. As you can see, 2.25 is not exactly great, but we could work with it potentially. And then we've got some preliminary apogee, max velocity, max acceleration values down here based on the class of engine that has been inserted to the rocket versus the size of the rocket, or excuse me, the mass of the rocket. So we could, you know, in a I hate to use this term because it can be a little bit confusing, but in a vacuum, we're not speaking in a literal vacuum here. We're talking about in a situation in which we're only taking into account the power of the motor versus the mass of the rocket. Our apogee would be 73.2 meters. Our max velocity would be 33.3 meters or 37.3 meters per second, which is about a tenth the speed of sound, at so Mach 0.11. And our max acceleration would be 171 meters a second squared. So at its fastest acceleration, it'd be going 171 meters a second squared. It'd be accelerating at a rate of 171 meters per second. At its fastest moving, it would be moving at a rate of 37.3 meters a second. So that is to say, it is under max acceleration for far less than a second, which is, I think, you know, I stressed on that point on last Monday. And then the apogee is 73.2 meters, which is not incredibly high. But again, this is all assuming nothing else. What do I mean by that? Well, our ejection delay could be too short. Like our rocket could still be coasting upwards and have not yet reached its apogee when the ejection charge blows. And then the parachute gets deployed and the rocket gets slowed down greatly. We don't know that until we start running some simulations. However, this information right here gives us a sort of a preliminary view of, you know, how the rocket would fly based on that. We would really want to get a final look in the flight simulations. But for now, you know, that gives us a basic idea. All right, I know that was a lot of review. In fact, that was half the class of review, but it's been a while since we've done it, and there was a lot of information that we went over last Monday, so I just wanted to sort of go through it again really quickly and make sure that we had all that there. Anyway, what we're going to do is we're going to add a few new configurations and put a couple of different classes of motors in there. A, because we want to see how the different classes of motors could affect this rocket, and B, because it'll be a good way to look at the motors menu again. So I just hit new configuration 4 times, which gave me 4 new configurations. As you can see, the configurations are all creatively called no motors because they have no motors in them, and the inner tube has no motor in it. Expected, you know, outcome. So I'm just going to double click on the first one. That is an empty configuration. And we're brought back to our rocket motor selection screen. Now, as you can see, I don't have a whole lot of things listed here because under the filter motors tab, I just have it so that we're only showing Estes motors. Again, not an advertisement for Estes. Just want to keep consistency among all of our different launch options. You know, if we start using different manufacturers and stuff like that, they're going to have different designations, and you know, their motors could operate a little bit differently. They're going to have, you know, different diameters potentially, and you know, anyway, we just want to run with the same manufacturer in order to keep consistency across the board. First one, I'm just going to single click over here on the B6 because we're going to add a B6 class motor. However, we're also going to we want to add a specific ejection charge delay to it. So it's automatically selected for. That's great. So I'm just going to hit OK. So now we have a new configuration with a B6-4 motor, and I'm going to go back in, and I'm going to select C5 or C6. C6. Ejection charge delay is 3. That's great. We want a C6-3 motor, so we're going to hit OK. So now we got an A8-3, a B6-4, and a C6-3. We're going to add 2 more configurations. However, these are just going to be different lengths of ejection charge delays on a C6. So I'm going to go ahead and double-click again. As you can see, our thrust curve is going to be C6, which is great. That's exactly what we want. However, under ejection charge delay, I'm going to go ahead and delete 0 and hit 5. So we've created a C6-5. then we're going to create a C6-7. So now we've got 3 different classes of motors, even though we've got 5 different configurations, because the C6s are all the same classes. The only thing we've changed is the length of the ejection charge delay. And again, that's because we want to make sure that we have a sufficient amount of delay after we run out of propellant in order for the rocket to reach its maximum height, because we want to let it coast upwards for a little while, because it's going to do that. It's going to have momentum that's going to take it upwards even after it's run out of fuel. So we want to make sure that the rocket is reaching its maximum height before we deploy the parachute. We also have the secondary bonus or positive or advantage or whatever you want to say of the fact that the rocket will be moving much slower if we allow it to reach its apogee, because as it's going higher, it's going to be slowing down, right? At some point, it's going to reach maximum height, and for an instant, a very small instant, that rocket will be moving 0 meters per second because its upward momentum will change to downward momentum, because then it'll start falling down, right? Makes sense. So the slower the rocket is going, the less stress the parachute and, recovery system and stuff like that is going to experience when it deploys. So we also kind of want to make sure of that. Because, it's just going to be not a great thing, if we deploy the parachute while the rocket is still going fast, because A, it's going to slow down the rocket and theoretically not make it fly as high, and B, we could damage the parachute if we deploy it while the rocket's still moving really fast. So we've got 3 different classes here, and for one of the classes, 3 different ejection charge lengths. Now I want to bring another thing to note. If we look down here in the little preview area, as we can see, we got our 73.2 for Class A. However, B6, we go all the way up to 177 meters, and it goes a lot faster. It's a 1/5 the speed of sound instead of a 1/10 now. It's almost double the speed. On our C, look at that, we're going a 1/3 the speed of sound. So it's even faster than a B. In addition, we're going even higher. We're going, well, somewhere between 2 to 3 times the height. And our acceleration is also pretty significant. So 363 meters up in the air, nothing to sneeze at. Like, that's some real stuff. So, again, this is all stuff that's assuming that we give the rocket sufficient time to coast upwards before the ejection charge blows, blah, blah, blah. Now, also keep in mind that the stability over here is changing. On the C, we're actually between 1 and 2 calibers, which is awesome. That's actually the magic area that we want to be in. A B, just outside of the range, and an A is a little bit further outside of the range. Now, this is not going to be like, horrible. It's not like these rockets are going to suddenly just vibrate out of control and go flying off into a building or, somebody or something like that. But it's just a little bit outside of ideal range. It could be improved upon, theoretically. But yeah, so these are some additional sort of things that are changed when you change the different class of motor inside of them. This is happening purely because the larger class engines are heavier, and so they're moving the center of gravity backwards, which means that it's getting closer to the center of pressure, which is affecting the stability. The only way we can affect the center of pressure is by changing the fins or the nose cone, which we've pretty much already done. Those are more or less set in stone, so at this point, from here on out, we're going to be adding a few more things to it, but those are just going to be affecting the center of gravity. So let's go ahead and go into rocket design, because we're going to add a few more things. The first thing we're going to want to add is an engine block. We want an engine block right about here to make sure that the engine doesn't fly into the center of the rocket the moment it launches, because the rocket won't go anywhere, and then the engine will just fly through the center of the rocket, and it'll just destroy your rocket, and that will make you sad. So we're going to add an engine block as a child of inner tube. So if I click inner tube once, I can add an engine block to it. Now, this engine block is going to have an inner diameter of 1.2 centimeters, and it's going to have a wall thickness of 0.3, which is automatically going to update the outer diameter. Well, it doesn't even Actually, the wall thickness was automatically updated because the outer diameter already existed. The outer diameter is the same as the inner diameter of the inner tube because it's slotted inside of the inner tube, right? So our outer diameter is 1.8, our inner diameter is 1.2, our wall thickness is 0.3, which is going to give us a decently thick engine block. The length is going to be, I believe, yeah, it's going to stay 0.5 centimeters. However, we're going to position it relative to the top of the parent component. We're going to add 0.2 centimeters. If I hit enter here, as you can see, it just gets placed right there, which is perfect. It's exactly what we want. So there is our motor mount right there, and that's just simply there in order to, keep the engine from flying in through the middle of the rocket. But we're not done. We're still going to add a recovery system. We need a recovery system. Well, we also need some centering rings. So let's go ahead and do the centering rings first. Excuse me. So if I click on the body tube, because I want to make these centering rings a child of the body tube, I'll have it selected. I'm going to go ahead and click on centering ring. The first one, I'm just going to keep as is. I'm not even going to do anything else. I'm just going to click close. So as you can see, we get a nice centering ring in the back over here. Now, a centering ring is simply a stability bit. You can think of it like, well, since the inner tube doesn't have the same diameter as the body tube, the inside of the body tube, as it stands before we put any centering rings in here, the inner tube is just sort of floating in empty air right here, which is cool, but it's not helpful. Like, that's not at all what we're interested in. We want to have a solidly anchored inner tube, again, in order to make sure that the engine doesn't go anywhere when it fires. So we start adding centering rings, which are just basically spacers which keep the engine block, or excuse me, the inner tube in there. If the inner tube changes in diameter, the centering rings in Open Rocket will automatically change their inner diameter as well in order to adjust. So if the inner tube becomes smaller in diameter, the centering rings will become thicker so that the inner tube will still have a tight fit. If the inner tube becomes larger, then the centering rings will become thinner so that the inner tube will fit in there, so on and so forth. We're going to add a second one though, because we want to make sure that we have enough stability. So this centering ring is going to be plus negative 4.5 centimeters off of the bottom of the parent component. So I had one that was 0. Now we're going to have negative 4.5, which is going to place it somewhere over here. If I hit close, it was a little bit further than I thought. But yeah, it was right about there. So now we got 2 centering rings. And again, those are just meant to keep the inner tube in place. Perfect. So we got that. Now let's go ahead and we're going to add a recovery system. So what do you think, based on the fact that we're making things that are connected be children of components that they're connected to? The centering rings keep their default values. Well, the first one keeps the default value all the way through. The second one keeps the default value except for the position relative to the bottom of the parent component, and then it's going to be plus minus 4.5 centimeters, which is sort of a weird thing to say. For sure. Yeah, so we are going to have a parachute, we're going to have a shock cord, and we're going to have some recovery wadding. What do you think that's going to be a child of in this tree over here? You notice how we've got the fins and the centering rings, a child of the body tube, and the engine block, a child of the inner tube. Based on where this recovery stuff is going to go, what do you think it's going to be a child of? Well, the parachute, the shock cord, and the recovery wadding are all going to go inside of the body tube, right? Now the shock cord is going to be connected to the nose cone as well as the body tube, but everything is going to be going inside of the body tube, so we have a common denominator there. So let's go ahead and make everything a child of the body tube. So we're going to start out with the shock cord. As you can see, we get this sort of dashed line area denoting the shot chord is just sort of an abstraction so that we know what we're looking at. Now, this is going to be positioned relative to the top of the parent component. We're going to add 2 centimeters to it. So we're actually going to move it past the shoulder on the nose cone. And that's because the shoulder on the nose cone is the exact same diameter as the inside of the body tube. So we're not going to have anything occupying the same space as the body tube. That doesn't really make any sense. Or the nose cone, because it doesn't really make any physical sense. So we want to make sure to offset it, because that's where it's going to be sitting on a rocket. Now the packed length and the packed diameter are not going to be the defaults. The packed length is going to be 5.2 centimeters, and the packed diameter is going to be 1.2, 1.2, not 1.5. So as you can see, we got this long and thin area now. So it's roughly double in length and roughly half in diameter. So plus 2 centimeters, packed length 5.2, packed diameter 1.2. And you get this little area right here. I'm going to go ahead and keep the shot chord length the default and the shot chord material the default as well. Boom, hit close. So now we've got our shot chord there. Now part of the reason why this is important is, as you can see, it's actually adding weights to our rocket. Our stability has actually changed from what it was before. The stability has gone a little bit higher because the center of gravity has moved just a wee bit over. Our parachute and our recovery wadding are really going to mess with that, but let's go ahead and add those anyway. So our parachute diameter, we'll keep that the same. Shroud lines, we're going to keep that the same. We're going to change the position on the packed length and packed diameter, though, just as we did before. So it's going to be plus 3.2 now, because again, we don't want it to be occupying the same space as the shoulder, because that's just physically impossible. So it's going to be sort of partway through the shot cord. Now, you might be going like, well, this doesn't make any sense either. Well, the shot cable is just that, a cable. So we're packing it with the parachute, so you can kind of think it's all just sort of packed in together in the same spot, since it's not a solid piece of plastic like the nose cone is. We're going to change the pack length and the pack diameter, though, so it's going to be 4.2, I believe. Yeah, 4.2 and 1.8. So as you can see, same deal as the shot cable. It's a little bit thinner and a little bit longer, and it messed with the stability quite a bit. Now the stability has gone all the way up to 2.3 calibers, and remember, this is our C engine. So this is the one that was between 1 and 2 calibers beforehand. So this is part of the reason why you want to simulate this stuff in OpenRocket as well. So we got a parachute. Now we're going to add our recovery wadding. Go ahead and raise your hand once you found the recovery wadding button. Because I'm a mean person, it took me a second to say this, but there actually is no recovery wadding button. Yeah, no, I know. There is no recovery wadding button, though. There is, however, a mass component button, which is just sort of a generic button for anything that's going to be in your rocket that has a weight, which is pretty much everything. Because there are a bunch of things you can put in your rocket. As your rockets get larger, you can, put inside like little telemetry components like an altimeter and stuff like that, and things that'll transmit to your phone so you can get information in real time, which is pretty cool. You can put an army man in there with a parachute of his own, so as the rocket deploys his recovery system, the army man gets shot out, and then he, his parachute deploys and he floats down gently alongside of the rocket and everything like that. So you can add stuff to it, but there aren't, it would be just a monumental task for the people who make this open rocket simulator to add buttons for everything. However, all of these things have something in common. They all have masses. So there's this generic mass component button, which will allow you to add a mass of some description to your rocket in some point so that you can account for the center of gravity, because that's something you've got to do. You've got to account for the center of gravity. If you don't account for all this stuff, and you just have like a rocket that has no recovery system or whatever in there, and then you launch it and you're like, well, it didn't perform at all like it was supposed to in open rocket. That's because your center of gravity is probably way different than what open rocket was guessing it had, and it's just, it's not going to fly like you simulated. But anyway, excuse me, the component name, we're going to call recovery wadding. Doesn't really need a name in order for it to work. However, this is for our purposes because, again, if we have, let's say we have like an army man and we have a little altimeter and we have a transmitter and we have, I don't know, a whole bunch of confetti on the inside that deploys when the rocket does. That's not meant to slow it down any. It's just meant to be like, party rocket, hooray! All of those things are going to take up mass, but none of those things are simulated here, so you're going to need to add a mass component for each of those things. Which means that if you keep all of them as unspecified, you're going to have a hard time keeping track of what's what when you're trying to come back later and figure it out. So you give it a name that's helpful. Yeah, it's kind of a fun idea, right? I kind of want to do that. Just add a bunch of streamers and confetti to the inside of the rocket so they all just kind of, shoot out whenever the rocket deploys this ejection charge. As you can see here, there are some, yeah, exactly. There are some generic ones, but we're just going to keep it as unspecified. And we're just going to go ahead and put in a mass and a position for it in the rocket. So it's going to have a mass of 2 grams. And as you can see, we got mass, approximate density, length, and diameter. Now, approximate density is derived from the amount of mass per size. So remember how we've had those things where it's like there are 3 parameters and you can adjust 2 of them and the third one will automatically update? Well, we've got 4 parameters here. You can adjust 3 of them and the 4th one will automatically update because length and diameter work together in order to create an area or a volume. Approximate density is weight per volume. So if we adjust the mass and the density and the length, the diameter will update itself automatically. If we adjust the mass, the length, and diameter, the density will update itself automatically, so on and so forth. So we're going to have a mass of 2, we're going to have a length of 3 centimeters, and we're going to have a diameter of 2.3 centimeters, which is going to give us a density of 0.16 grams per centimeter cubed. And it's going to be plus 8 centimeters from the top of the parent component. And this is going to move the center of gravity a little bit back from where it was before, but it's still going to be way forward, as you can see, 2.42 calibers. So we got a mass of 2 grams, a length of 3 centimeters, and a diameter of 2.3 centimeters. And its position relative to the top of the parent component is going to be plus 8 centimeters. So we're going to hit close. We've got one more thing to add. It's going to be our launch lug, because you got to have a launch lug. Launch lug is going to have a length of 3.5 centimeters. It's going to have an outer diameter of 0.7, inner diameter of 0.5, and a radial position of 19 degrees. Just so it's not on the same plane as one of the fins, because if you try to, if you're trying to put the launch lug onto a launch rail and there's a fin in the way, it's kind of annoying. So we offset it from one of the fins a little bit so that the fin isn't in the way. I know I went through that last bit in the end pretty quickly, but our rocket is done and ready for simulation, which is what we're going to do on Wednesday. Because we're pretty much out of time at this point. So, yeah, sure, for the measurements for, hold on, let me expand the question box so I can actually see that. The measurements for the launch lug? Or the measurements for the recovery wadding? Or at any rate, I'm going to go ahead and skip the poll questions since we're very close to the end. We'll just leave it open for question and answer time, including, going over the measurements again and stuff like that for everybody. But yeah, if you don't have any questions about anything, you're more than welcome to head out. Have a wonderful couple of days, and we'll see you on Wednesday.